Today's workshop is an ESTCP tech transfer effort. It is a FAQ, or frequently asked questions, on perfluoroalkyl and polyfluoroalkyl substances, otherwise known as PFAS. I'd like to introduce my co-principal investigator, Jennifer Field, who's the leader of the pack from Oregon State University, Jason Conder from Geosyntec, and Chris Higgins from Colorado School of Mines. So the way we're going to do this today is we're going to take turns answering the FAQs that we've identified. But first, I'd like to refer you to the project number. It's ER 2015-74-T2. And if you visit the CERDUP ESTCP webpage, you can download important deliverables from this project. So with that, these are the 8 questions that we're going to answer for you today. And Jennifer is going to lead us off with the first question. Jennifer?
It's my pleasure to leave off on the first question, and that is, what are per- and polyfluoroalkyl substances? So first, take a look at the cartoon in the upper right-hand corner. This is a molecule many people know now. It's PFAS, or PFOS, perfluorooctane sulfonate. And that cartoon is showing you some really unique attributes to many of the chemicals in this class that we're calling PFASs, or per- and polyfluoroalkyl substances. PFAS is a particular example, and it's one of those for which we have an EPA health advisory level. You'll hear a little bit more about that later. If you examine this molecule, you'll see that you very quickly pick up the carbon backbone that is entirely set with fluorines. There's no hydrogens on that carbon backbone. You also see the other attribute, which is the sulfonic acid head group, and we've drawn that in the water. And so here we have this fluorinated tail, a highly fluorinated tail sticking up out in water, and this polar head group in water. And this is showing a type of behavior for which PFAS is well known. You can see that that assembly of carbon and fluorine bonds has given it rise to a pretty unique nature of a molecule. So that carbon-fluorine bond is super strong. It's the strongest in nature. And when you assemble a number of those together, you get interesting properties, both from a functional point of view. So for example, the oil and water repellency that you enjoy in articles in commerce, textiles and papers and such is in part due to that, large part due to that fluorinated tail. On the other hand, some of the properties become a little less predictable in the environment and in the laboratory environment when you have so many carbon-fluorine bonds assembled together. And PFAS is an example of a perfluorinated compound. It's a pretty strict definition. It means that all those carbons have only fluorines and not hydrogens. And so this is why we're advocating a change or an awareness in terminology. If you look at the perfluorinated term, it really means something quite specific. But if you go to the molecule in the lower part of the page, this is another chemical that's found in mixed situations where we have an aqueous film forming phones, which is the subject of today's webinar. And you see that this fluorotelomere sulfonate has a different attribute. There's 2 carbons that have blue hydrogens on them. What you're seeing is a polyfluorinated molecule. It's not strictly perfluorinated. Now, is this just semantics? No, it's not. It turns out that those 2 carbons that have hydrogens on it represent a weakness in that molecule. And it turns out the fluorotelomere sulfonate is biodegradable, and you can also oxidize it. And that's very much in contrast to PFAS, which cannot be easily oxidized and is not biodegradable. So that small distinction in the chemistry actually has implications when it comes to the environment. And so right now, what you see is an international acceptance of the use of per- and polyfluoroalkyl substances for any settings when we actually have a mixture of things like PFAS and PFOA, which is perfluorooctanoic acid, and things like the telomere sulfonate. When they're all there together, we really can't use that term up in the upper right corner, perfluorinated chemicals, because it really doesn't work. So if we do take a closer look at PFAS and PFOA, what you'll notice, of course, is they're anionic. They're anionic at all environmental pHs and physiological pHs. That means you and me. And what I mean by that is it's a pH range of 4 to 10. These are very strong anions. So what does that mean with regard to their behavior? Well, first of all, those strong acid groups are deprotonated. They're an anion. So that means that the molecules to which they're attached are not volatile. This is why we can't use things like gas chromatography for their measurement. This is why we can't airstrip them out of water. So they're really anionic. And also going right hand in hand is they have very high water solubility. That's why we see them transport readily in the environment. And that's why we see them pass through sediment in soil and into groundwater. Now, quite a few people might be wondering, why are they emerging just now? We've used aqueous film-forming foams for quite some time, decades, going back to the 60s. Well, the problem is, just what I told you, they are anionic, so we couldn't see them with gas chromatography mass spectrometry, which was the common tool used to characterize sites and look for volatile priority pollutants, like you might be familiar with pHs and PCBs and dioxins. So when we used this tool for early site investigations, we couldn't see them. However, there were quite a few field reports. People would say, wow, you know, the groundwater foams when I'm collecting it, or when it rains here, the soil actually foams. These were all important clues that we had persistent chemicals still present in these